Hey there, Year 12 General Maths. Here is your holiday homework for exercise 2G, the coefficient of determination. I'm recording this Wednesday of the last week before the cycle break. So if you hear any background noise, it's probably Tilly or Jess. I can see them right now. I don't know what they're doing. Something weird. Anyways, what we'll be looking into is calculating the value of what's called the coefficient of determination. So this is a new concept for you guys, and you want to be able to use this coefficient of determination to assess the strength of dissociation in terms of explained variation. So it's a very, I just waved at Tilly, it's a very specific thing that you're using this for, and it does take a bit of time to grasp it or to understand it, especially with the term variation and its purpose. So recalling our associations with your R value. So these are the different types of associations that you can have. So there's 3 levels: strong, moderate, or weak. And then there's the direction, whether it's positive or negative. If there's no association, it lies within the interval of negative 0.25 to 0.25. And these things here are associations. They're used as a guide to determine if there's an association between one variable to another when you create a scatter plot. So we've gone through this with our calculators and how to determine the R value if given data points for 2 different variables. But what we're going to do now is take it a step further in terms of what we can do with this R value, something else that we can do. So the coefficient of determination is the degree to which a particular variable can be predicted from another linearly related variable. So linearly being a keyword. And this is given by a statistic called the coefficient of determination. And it's calculated by getting your R value and squaring it. So the math behind it is actually quite simple. It's the interpretation of what this number actually means. It's going to take you a while to wrap your head around it. So let's just do the math part for now. Let's say there is a correlation between weight and height. And this correlation has an R value of 0.8. So going back, 0.8 lies within this interval here. So there is a strong positive association between weight and height for this particular sample of people. And what we're going to do is we're going to find the value of the coefficient of determination. And we'll talk about what it means. We'll just try to figure this out. This is really simple. If our R is equal to 0.8, all we are doing is grabbing our R value and squaring it. So grab your calculators out, and we are going to do 0.8 squared, and this is equal to 0.64. Now this, as a percentage, you would just times this by 100. So our coefficient of determination is 64%. So I want you to keep this number in the back of your head when looking into the next example and how we can use this 64% as a tool or as a guide in terms of relation between weight and height. So the coefficient of determination as a percentage, has to be as a percentage, tells us, and this is going to be a bit confusing at first, tells us the variation in the response variable that is explained by the variation in the explanatory variable. So when you create a scatter plot of some sort and you were to put this, there's your linear regression line and there's a scatter plot that has a pretty strong association. What this number here, this 64%, is saying, it tells us that the variation in the people's weight is explained, the weight in the response, is explained by the variation of height. So what does that 64% mean? So that just says that we take 64% of these people within here. and the variation, so how varied those numbers are. So the way that they are deviated away from your average, that deviation or the variation, that scatter, is determined by the scatter of the weight. Okay, so determined by the scatter of the weight. The more scattered or the more varied or pushed away people's heights are, the less reliant weight is as a coefficient of determination, something that determines that. Now, the way my brain tends to think about this when I first looked into this is, let's take the opposite of this. Let's take the 36%. The rest of the variation, so 36%, in weight will be explained by other particular factors, maybe such as diet, lifestyle, or the build, many other different factors. So we can say that 36% of the variation in weight is not explained by the variation in height. So these heights here vary or scattered for a particular reason. 64% is based on the scatteredness of people's weights. So like almost like a reliance of the scatteredness of weights, and then the other 36 are based on other factors which we don't know. Okay, so this is what the coefficient of determination means. We'll take another example. Let's say that there's a level of carbon monoxide, and this is measured in the air at a roadside, and the traffic volume is also measured at the same location, and there's a linear relation. We have an R value of positive 0.985, and what we're going to do is determine the value of coefficient of determination, write this as a percentage, and then interpret what this actually means. In this particular relationship, the traffic volume is the explanatory variable. So the traffic volume will explain the level of carbon monoxide. So we know that there's a strong link or strong association, very, very strong. It's at 0.98. Our coefficient of determination is squaring this number, and we get 0.9702, which is 97% rounded to one decimal place. So we can say that when this scatter plot is put into play, it's pretty darn close to that regression line. There's not much variation or deviation away from that average. So we can say that 97% of the variation in that carbon monoxide, like that little bit that kind of strays away, 90% on that variation in carbon monoxide levels in the air can be explained by the variation in the traffic volume, because that traffic volume also doesn't have that much variation to it. Okay, they're pretty close to that line, so we can say 97% certainty, if you want to use that as a word, of a variation between one is explained by the variation of the other. Maybe the other 3% could be other stuff like any other carbon monoxide that can contribute to that particular area, but it's pretty clear that it is coming from the traffic volume. Now what we're going to do is calculate the correlation coefficient from the coefficient of determination. So let's say that the coefficient of determination has been given to you this time, which is 0.5210, and we want to work out what the correlation coefficient R is. So we've got our determination, now we want to work out how do we get R, and this is just by doing the opposite. So we know what R squared is in this case, so we are going to try to figure out what R is, and all you need to do is square root what that number is. So we end up with a positive or negative 0.7218. Remember, when you square root a positive number, the result can either be positive or negative. But given that we've got context that there is a downward trend, it's safe to assume that this here is a negative association. So our R value is negative 0.7218. That is it for that exercise 2G. It's page 148, and you are doing questions 1 to 3.